All right, on this beautiful day, we are going to use multiplication counting principle without replacement. So last week we did with replacement. This time we're going to do without. My apologies for the you see what the irony there? I left out the out. I know, crazy talk. I know. All right, so this is new probably to most of us of what the idea of this exclamation mark means. And it is, we say it factorial. So n factorial is a product of an integer and all the lower ones until you get to 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, and it's 120. So evaluate each of these ones here. So if we want to evaluate what f looks like, remember that it's 2010 times 2009 times 2008, etc. Now I'm not going to write them all over 2009 times 2008. Now notice that all of these drop out except for the 2010. Exactly. Okay, now same thing here. Watch the magic on this one. 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 7 times 6 times 1. Why didn't I write that? Because 9 factorial drops out with 9 factorial. And 3 factorial, we already know, is 3 times 2 times 1, or 6. So now notice what happens. The 3 and the 2 can drop out with that. And so now I have 2 times 11 times 10. So 2, 2, 0 is your answer. So on this lovely day, we're going to talk about something called permutations. I do want to give you a heads up that you have something on your lockers called a combination lock, but it is wrong. It should not be called a combination lock. It should be called a permutation lock. Okay? Why it's called a combination lock? I don't know. Because ultimately, we're not talking about combination of numbers, which is like a group of numbers just thrown into a backpack. We're talking about permutation, which is extremely important, that order is important. Order is important. So let's take a gander at this. Imagine you have 10 books. You've ever heard of these things? They're like made of paper. And anyways, so you have these 10 books on your bookshelf, and you're going to read 3 of them this summer. Now, since we're talking about I read one book, then I read another, and then I read another, some of you probably read them at the same time, but let's assume that order is important. I read a book, then I finish it, then I pick another one up. So the question is, how many different ways can you read the books? So let me think here. If we think about position, this is book 1, this is book 2, and this is book 3, right? How many different choices do I have to begin with? Well, in this first one, I have 10 books to choose from. But once I've read a book, do I still have 10? Well, yes, I still have 10 books, but only 9 of them I'm going to consider now. So now I say my first rodeo out is I have 10 options. Now I have 9 options, but now since I've read 2, I only have 8 options here. So this is how we can represent it. You don't need those boxes. These boxes just give you like placeholders, 10 in this spot, 9 in this spot, 8 in this spot. And it subsequently goes down as you complete the books in terms of the number of options I have. So as we multiply together, I have 720 different options for my order. So how many different ways can you select 4 cards from a deck, a standard deck? Standard deck, of course, has 52 cards. And you don't replace the cards. So this one here, 52 ways. So we're not looking for probability of selecting a certain amount. What we're doing is seeing how many options we have total. So I have 51 the first time. I don't replace it. 52. So then 51, then 50, and then 49. Equals 6,497,400,000 different ways. So this next part here, an arrangement of teams or objects or symbols, whatever we're talking about, cards or cats or books, and we don't replace them. It is called a permutation of those objects. So a permutation lock tells you about the numbers being permutated. The permutation of books, the permutation of cards when you select 4. So the number of permutations taken, of R objects taken from a group with n distinct objects. Like I said, we have 10 books, and I'm going to read 3 of them. So 10 books, R is 3, is denoted by this right here. So these are kind of like exponents, but hanging out down below. So just so that you see the perspective up here, I would say 10p4. So that situation is 10p4. I have 10 books, and I'm going to read 4 of them. Down below is I have 52 cards, and I'm going to choose 4 of them. So, and these 2 formulas can be used to evaluate. Number 1, you can just start at n, whatever n is, like we did, 10 times 9 times 8, and you go down until you have R numbers. So remember what we did. With 10p3, we started with 10 and then 9, and we stopped at 8. Why did we stop at 8? Because I have 1, 2, 3 numbers. So this is R numbers.
What would you write if you wanted?
The question is, what would I write if I'm going all the way down? There's 2 ways to write that. 10p10, which is, and that's what we're going to look at the very end, that just simply means 10 factorial. We just go all the way down. Now, this one works decently, especially when R is relatively small. So I only had 3 numbers to write down. But if I had a more complex situation that said this, 52 cards, but I want 25 of them, that requires me to hit the 52 times 51, but all the way down until I have 25 numbers multiplied. So is there a faster way to do this? And the answer is yes. Here is the formal definition of permutation. And it simply says this. Whatever your n is, that's your factorial, but we divide it by n minus r factorial. So in the case of where I had 10p3, we write this, 10 factorial divided by 10 minus 3 factorial, which simplifies to 10 factorial over 7 factorial. And as we saw earlier, 10 times 9 times 8 times 7 factorial divided by 7 factorial. And the factorials, the 7 factorials drop out, and we're left with that. And you're like, Swenson, that's more work than I wanted to do. You're right. It's more work because 3 is a small number. If your R is a smaller number, 2, 3, 4, 5, something like that, then this one over here is a great method. It's when R gets to be a little bit more obnoxious that this actually makes more sense. All right, so let's take a gander at this next one here. And we're going to solve this one using both methods. How many different 6-letter strings can be formed from 6 letters in the word palindrome? Notice that every single letter, by the way, is different in palindrome. So that helps out. And we're not going to replace.
Is that uncommon?
Let's see what this is here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 total letters. I'm going to do permutations because it's about order. And then I want 6 of them. 2 ways for you to do this. 2 different methods. Number 1, we can just say 10 times 9 times 8 times 7 times 6 times 5. Why do I stop at 5? Because 1, 2, 3, 4, 5, 6. I have 6 numbers. That tells me when to stop. I don't stop at 6. I start when I have 6 numbers. The other way to do this is we can just set it up and put it in the formula. 10 factorial over 4 factorial. I could just jump to 4 factorial. Now, if you're using a calculator, this can be sped up fairly quickly. Actually, both of these, but both of these are equally valid, especially with the calculator. So let's see and go ahead and just plug in. So both methods yield the same result, and using the factorial button on your calculator will speed things up. Or in this case, since R is relatively small with 6, then just punching it out is just as fast. In the Soissons National Art Museum, there are 12 Renaissance painters, and actually paintings, I guess, would be a better but only enough room to show 8 of them. So how many ways can the paintings be arranged on the wall? So clearly we see that we have 12 to begin with, P and 8. So 2 ways to do this, but if I did do 12 times 11 times 10, that's 8 of them to write out, so it gets kind of obnoxious. So I could do 12 factorial over 4 factorial, and then plug that into my calculator. So as we do this, we do get a very, very large number, 19,958 and 400. 11p5 is straightforward. If I wanted to multiply it out, I can say 11 times 10 times 9 times 8 times 7. And I could do that because there's only 5 numbers, so that's a fairly fast process to get my result. But what would be a good scenario that can describe this? We could say something like, all right, well, we have a class of 11 kids in a music band, and 5 of them are going to go in a marching band, and they're going to be walking one in front of the other. So that will be an order situation. So this one here gives me 96,909,120 different ways. The last thing that we're going to look at is just a quick application on how, not application, but more of a taking it to the next level for solving. Okay, so here we have NP6 equals 17 times NP5. In other words, a permutation of 6 is equal to a permutation of 5 just times 17. So how do we solve this? Well, first off, we need to know what we mean by things. Remember what this means right here. This specifically means n times n minus 1 times n minus 2. And I'm going to go do this until I have 6 numbers total. Minus 4 and n minus 5. So let me count them up. 1, 2, 3, 4, 5. I have 6. Equals, and I'm going to interpret what that means. That means n times n minus 1 times n minus 2, n minus 3, and lastly, n minus 4. Now the fun part. Notice that if I take this, I need to get n by itself, so I need to collect all my n's. So I'm going to divide this entire side by the red here, okay? But just notice that when I divide by n, the n's drop out. When I divide by n minus 1, n minus 2, n minus 3, n minus 4, and what are we left with? We're left with n minus 5 equals 17. So what does n have to be? N has to be 22. So, in other words, the original group that I have is 22, and I pull 6 from that. 22, and I pull 5 from that. And now we can just do a quick check with our calculator. We have it set up here. We see things that drop out. Now you can use your wonderful world of multiplying out here. So I get n squared minus 7n plus 12 equals 20. N squared minus 7n minus 8 equals 0. And now we're in a position to factor, quadratic formula, or some other method here. So I'm going to snowflake right here. So remember, snowflake says take the a times the b, so I get negative 8 goes on top. The b goes on the bottom, negative 7 goes there. I'm going to put n's in the wings right here. In other words, I'm just taking this guy and splitting it up. And now I ask myself, what two numbers multiply to negative 8 but add to negative 7? They have to multiply this way and add this way. And clearly there are only two numbers that do that. Negative 8 and positive 1. So when I do, I have this factored. So I have an n minus 8 times an n plus 1 equals 0. The zero product property says I can split those up. So n minus ochito and an n plus 1 equals 0. Now clearly, One of these has to be the answer, and one is not. This here is called an extraneous solution because I can't have a group of negative numbers. So clearly n has to be 8.
Makes sense. Wait, can you?
All right. The last two things we want to look at is that if you have a group and you want to figure out how many ways you can grab that same number of group, the answer is just n factorial here. So I have 10 people, and how many different ways can I order them? And it's just 10 factorial. And the last one is a definition. It seems illogical, but this is actually one.